Good morning. This week you'll be covering sedimentary rocks and sedimentary processes in laboratory. I'm going to give you a little bit of an overview of some of the material that will help you have a more comprehensive understanding of the laboratory and also allow you to complete the lab in the hour and 40 minutes that you will be given to complete it. Now, we just finished a discussion and lecture on weathering, and I've introduced sedimentary rocks to you. You remember that with weathering, we have weathering byproducts. Weathering byproducts consist of both sediment and dissolved ions that are in solution. And consequently, when we're looking at sedimentary rocks, we have to look at these weathering byproducts. And sedimentary rocks are formed in environmental settings or depositional basins where both sediment can accumulate or chemical precipitates. And as you see in the slide here, you can see a river system that is flowing into an embayment there. You can see clearly the river is transporting sediment itself along its channel. You can see within the water column itself suspended silts. What you can't see there, of course, are dissolved ions. And you know that rivers transport salts and other dissolved materials that can reprecipitate in an ocean setting or in other settings. Now, sediment and chemical precipitates will accumulate in sedimentary basins, as we discussed earlier. This slide here shows you a number of different sedimentary basins. I don't want to go through all of them right now. You'll be discussing some of them in the laboratory. But clearly, when we're looking at concentrations of sediment, the ultimate basin is the ocean itself. There are a number of transitional basins like lakes or floodplains of rivers. Clearly, in glaciated valleys, you can have sediment accumulate as morainal deposits. There's a whole range of different depositional settings where we can have sedimentary rocks form. What's interesting is the nature of the environment. The depositional setting itself can tell you something about the mechanism of how the sediment is transported. It can sometimes tell you something about the source rock, where the sediment was eroded and where it came from. And these are all important factors that we use when we're reconstructing paleo environments. Sedimentary rocks are ideal for those kinds of reconstructions. Before we look at reconstructions, let's look at how a sediment is taken and lithified in the sedimentary rock. Now, when we're looking at the evolution of sedimentary rocks, there are three processes where sediment is converted to sedimentary rocks. There is accumulation, and accumulation of sediment is going to occur in depositional basins. Over time, sediment will continue to accumulate. You will have thicker and thicker sequences of sediment. Eventually, you're going to be burying the lower sediment units. And as you bury that sediment, you're going to start to compact it. That's the initial process of lithification. Now, over time, you will continue to accumulate thick sequences of sediment. Within the sediment itself, there'll be void spaces. Groundwater will move through that. Within the groundwater, you'll have dissolved ions that can precipitate out and actually cement the sediment class together. These are your cementing agents, and the process is cementation. Now, this slide here shows you a typical sandy sediment, which will be lithified into sandstone. What you'll note there, as you initially accumulate the sand, it's going to have large void spaces between it. It is not going to be very compact, as you can see here. Now, as you add more and more sediment on top of that, you're going to start to compact it. The void spaces are going to get smaller. What's going to happen here, any dissolved groundwater is going to start to fill in completely these void spaces. Within that groundwater, you are going to have dissolved ions. Now, you can change clearly the solubility of that groundwater by adding more concentrations of dissolved materials. You can change the pressures, you can change the temperature, and what can happen here is the dissolved ions can cement out and form cementing agents and cement the sediment grains together. Now, there are 5 major cementing agents that are capable of cementing class together. There is silica, which is easily diagnostic in the field because it tends to be clear. It can be confused with calcite, which is also clear, but everyone knows how you can identify calcite. You have an acid bottle with you in the field. You drop a little drop of hydrochloric acid on it. If it fizzes, it's calcite. If it doesn't fizz, then it's silica. The other cementing agents, iron oxide, really easy to identify in the field. Iron oxide has a reddish-orange stain to it. So if your sandstone or your sedimentary rock is cemented with a reddish-orange coloration, then it's likely iron oxide. Tars, organics, are also very diagnostic in the field. Tar sands tend to be dark black to dark brown. The organic matter or humic material in it leaves this dark coloration. So a sand that is cemented with tar is going to be very dark. Finally, you have clays. Clays look kind of powdery. They tend to be more weakly consolidated. So you can take the sand, you can kind of rub your finger on it, it'll start to abrade off, and you'll be able to see that powdery residue from the clays that cement it together. Now, if you're in the field here, here's two different sandstones, and just to test you here, you can see the one up here is cemented with a clear cementing agent. There's a little bit of oxidation here, but for the most part it's clear. And the one down here is reddish, the staining of this sandstone. So once again, this one really easy. Iron oxide, and up here it's either calcite or silica. I know this is silica because this is a sandstone that I've worked with before, but we drop acid on it, doesn't react, it is silica. Okay? Now, we can also have cementation of clay particles. Accumulation of clays in very low energy environments such as the open ocean. This clay will tend to accumulate over time. And what happens here with clays is originally, as this material starts to accumulate, these clay particles are going to be randomly organized. And you're going to have edges up against flat faces. But as you keep adding more and more weight to this, you're going to start to have these clay particles start to align themselves. And what's going to happen here is they're going to be more efficiently packed. And so with clays, as you start to accumulate and you start to compact and lithify them, they will be lined up with a preferred orientation, and you end up with these natural splitting surfaces. When you start to lithify clay sediment, you form the rock shale, which you'll learn about shortly. When that shale gets metamorphosed, it becomes slate. But what's important about this is these splitting surfaces get retained in the rock. And it's one of the diagnostic properties when you look at rocks that are formed from clay particles. The shale rock being shown down here on the bottom right-hand side of this slide. Now, what are some of the other properties of sediment that we look at? This is a cobble bed in a river channel. There's some things that stand out here. Clearly, the grain size. How big are these cobbles? Would you expect a wind to be able to transport cobbles of that size? And so clearly not. You might say, well, maybe a hurricane or a tornado, but for the most part, when you're looking at wind deposition, wind can't transport as efficiently as water. And so when we're looking at grain size, it tells you something about the energy regime of the transport agent. In this case here, we'd be looking at a stream that would be moving very rapidly when it has water in the channel. This clearly is a stream that's ephemeral, meaning that it's seasonal, that there must be high water discharge and very low, as you see here. So the grain size tells you something about the energy regime of the transport agent. Other factors and characteristics we can look at of sediment as it's deposited. The degree of sorting. When we're looking at the degree of sorting, we're looking at the grain size distribution. Is the grain size distribution the same throughout a depositional unit? And if it is, we say it's well sorted, meaning that the depositional body or the agent that's depositing it has a certain energy, okay, that it's transporting sediment of a certain grain size. As that stream starts to slow down, if it is stream or wind, it'll deposit sediment of a given grain size depending on that particular energy. Now, we refer to sediment that is of the same grain size as being well sorted, as this well sorted beach sand, well sorted river sands, well sorted dune sands from wind. Now, on the other hand, we can look at poorly sorted sediment. And ice, glacial ice, very commonly will deposit sediment indiscriminately. It will not transport sediment and deposit it according to grain size. When ice melts out, it will drop a clay-sized particle right beside a boulder. and that will get laid down. And so glacial sediment, glacial till, tends to be poorly sorted, as you see in the bottom photo on the left-hand side. So that is degree of sorting. Another sediment characteristic we can look at is the degree of angularity or degree of roundness. And again, this science makes sense. The greater the distance of transport, the more the sediment is transported, the more it's been tumbled and abraded. So you're going to tend to see a well-rounded when you've had greater distances of transport of sediment. If the sediment is transported really close to the source, like a landslide or a debris flow or some agent that is not going to transport the sediment a great distance, you're going to see that the sediment grains are going to be more angular. So this can tell you something. When you're looking at sedimentary rocks and you're looking at the angularity of the sediment grains, it can tell you something about the distance of transport. A few other things that we can look at that's kind of cool. You can determine paleo flow directions, in the case of streams. We have a feature that we call imbrication. Here's a series of clasts. You can see that they're sort of stacked up here haphazardly, and the current is flowing. What eventually happens here is the current is going to tip these clasts over with the long axes, and they're going to piggyback on top of one another. This is referred to as imbrication. It's just one example of being able to determine paleo flow direction, or telling us a little bit more about the depositional environment. Now, we're not going to cover all of these in this laboratory, nor are we going to cover all of these in this class. I certainly hope that you take other classes. Some of you might minor, some of you might major. You take this information and you learn about this in depositional environments. And so it's really kind of intriguing, the kind of information that can be conveyed by the alignment, if you will, of the class of this fluvial or river conglomerate. Okay? Now, when we're actually looking, of the actual classification of sedimentary rocks, which is a main topic of this laboratory, you're going to learn that there are three major classifications, subdivisions that we look at for sedimentary rocks. This is a little bit more detailed than the one you have in laboratory, but it more or less shows you the same material. We're going to subdivide sedimentary rocks into clastic sedimentary rocks, which are comprised of fragments of other rock, sediment that accumulates, fragments of other rock that gets broken down, accumulates. Clastic sedimentary rocks are subdivided based on grain size. And they are ranked here at the top here from sedimentary breccia to conglomerate down to progressively finer grains till you get to mud, or clay. And then if you look below that, we have something called bioclastic and chemical, and then strictly biological here. Bioclastic sedimentary rocks are those rocks comprised of fragments from living organisms, like clamshell fragments, or maybe pieces of microscopic organisms that might die and rain down onto the ocean floor, like chalk is formed of microscopic calcareous or calcite organisms. The third of these classifications are chemical sedimentary rocks. These are sedimentary rocks that precipitate directly out of solution. These are chemical precipitates. These are simply classified based on composition. Limestone is comprised of calcite, and you can see here dolomite is comprised of dolomite, which has magnesium in it, a little bit like calcium carbonate, except it has magnesium. Chert is comprised of pure silica, and then we can have evaporite or rock salt, halite, and gypsum being another evaporite deposit. And then finally, we can have a biological deposit that's comprised of compressed plant debris, which is coal. So those are the main subdivisions. And so just looking at these briefly, you can see a conglomerate is going to be comprised of rounded, large class that are going to be pebbles to gravel in size. They're going to be rounded or sub-rounded, defines the conglomerate. If the clasts are angular and large, you'd call it a sedimentary breccia, and you can see clearly the degree of angularity, and you can discuss in laboratory what environmental setting you'd expect to see this in. Clearly, it tells you something about distance of transport. As you go to smaller clastic sedimentary rocks, you go to sand-sized particles, and clearly in laboratory, you're going to look at different types of sandstones. Some sandstones are described as mature sandstones. Those are the sandstones that have been transported over great distances. They're going to tend to be largely comprised of quartz, because quartz is the mineral that's most resistant to weathering. There are other sandstones that you're going to look at that are going to be comprised of mineral grains that, that include other minerals besides quartz, such as micas or lithic fragments, and these are your mineralogically immature sandstones because they've been through, if you will, not as much of an intense weathering regime. The more weathering that a sediment will go through, the more likely you'll have greater and greater concentrations of quartz. Okay? So all this you'll look at in laboratory. Keep getting to finer class, you go to silt-sized particles. And silt-sized particles are going to accumulate where? In depositional environments are going to have lower energy regimes, like lakes or embayments and so forth. Okay? And finally, you're going to get your finest clastic sedimentary rocks. These will be your clays. Where will clays accumulate? In the open ocean. This is where your shale forms. Very fine particles. These are going to settle out very slowly in an ocean basin because the clay minerals can remain suspended, okay, for a period of time, and they will settle out in the deeper ocean basin settings. Now, your chemical precipitates. These are subdivided based on chemical composition. These, you have to learn about the chemical properties. Halite or rock salt, well, it's going to taste salty. You're going to learn to recognize it. You might actually, under a microscope, be able to see the cubic crystals of the salt grains. I don't recommend you lick everything. People throw acid on this stuff, so you'll just have to learn some of these features. Where do salt deposits form? Clearly, we can have salt deposits form where you have initial rifting of continents and shallow ocean basins. You can get evaporite deposits, and eventually those evaporite deposits over time, they can form salt diapirs along continental margins. And the reason this is so important is because this has an economic significance. These salt domes actually act as stratigraphic traps, if you will, for oil deposits. So a lot of you might wonder, why we have so many oil deposits in the Gulf of Mexico. Well, we have the oil there because of the original carbon-based material in the marine organism, but why they're trapped there is because of these salt domes, which have very low densities that rise up into the rock, and they trap the oil deposits in there. Just a little bit of an aside, but I think an interesting aside. Other features you can look at here, fossiliferous limestone, where you actually can recognize the clam fossils present there. This is a biogenic, derived from life processes. And you can also have inorganic limestones, where directly the calcium and bicarbonate ions can combine, and they can precipitate directly out into an ocean basin. As I mentioned earlier, you can have microscopic calcareous organisms that can die and rain down on the ocean floor. This is how chalk forms. The White Cliffs of Dover, the famous White Cliffs of Dover, are actually sedimentary rocks that are comprised of chalk, these microscopic calcareous organisms. Now, clearly, there are other features that we want to look at here. And some of these are depositional settings, where you start to have sediment accumulate. And so we're going to want to look at some of the sedimentary structures. You may wonder, why is sediment deposited in horizontal layers? Why is it stratified? And clearly what we're looking at changes in depositional events. This can be due to changes in discharge rates of streams. This can be due to, seasonality, where you might have high sediment fluxes into lakes and low sediment fluxes in the wintertime. It can be longer scale. You can have changing climate, where you might have organic rich sediment being deposited in warm climates, or during glacial climates, organic poor sediment, leaving you these different stratigraphic layers. This clearly is not, this is the painted desert. This is not a glacial environment here, but this is an environment where you have these depositional layers preserved in the lake. Some of them due to changing discharge rates into the lake. Some of them due to volcanic eruptions that might put volcanic ash layers. Some of these due by different chemical weathering processes. You might have a lot of iron weathering where you get this iron oxide deposit. Here you have a lot of organic rich sediment here. And so clearly we're going to see within sedimentary rocks, you're going to see also depositional layers, and you're going to see sedimentary structures. We're not going to cover all of these now. I simply want you to have an overview of some of the major ones that you'll be looking at in laboratory today. Crossbeds. How do crossbed forms? Crossbeds form where you have migrating stream systems. The stream, in this case here, in if you hear this is a meandering stream, it will erode towards the outside of the meander. We talked about this in lecture. It deposits towards the inside of the meander. And so what happens here, as a stream flows down on its floodplain, you're going to get erosion of pre-existing sediment, and then you're going to get redeposition of sediment that will be oriented differently. It is this difference in orientation that forms these crossbeds. And so again, you see crossbeds in the field when you're out mapping. Okay, we're probably looking at a migrating stream system, or as I discussed in lecture, perhaps maybe it is a migrating sand dune, where you have sand dunes, wind changing direction, and these sand dunes migrating back and forth across the sand desert there, and you're going to have these distinct truncations of these different orientations depending on the direction that the wind was blowing, excuse me, and the sand dunes were being deposited. Now, one of the other sedimentary structures you'll see in laboratory are mud cracks. We show you some 1 billion-year-old mud cracks collected from the belt group rocks in Montana. We know from clearly modern-day examples of how mud cracks form that we can use the present to the key to the past, that we can see how modern mud cracks form, that you have a lake that dries up, the clays or the silts in it shrink, leaving these desiccation cracks. Wind can blow sand into it, or even a lake can form, or maybe water can deposit sediment and bury the mud cracks. They get preserved over time. They can become lithified. Later you can erode, or uplift and erode, and expose them again. When you find them in the environment, oh, that's mud cracks. What does that tell you? That environment must have been desiccated. It must have dried out, perhaps suggesting that there's a seasonality to this area, or a long period of desiccation where it dried out. And so mud cracks are indicative of a semi-arid environment, or clearly where you're getting some desiccation of your water body. The last thing that I want to mention here are the fact that when we're looking at sedimentary rocks, they are great for preservation of fossils, particularly the fine-grained sedimentary rocks, the mudstones or shale and siltstone, because it is these types of sediment that have very few void spaces. They don't have a lot of oxygen present, and so any fossil or even soft-celled material or hard-shelled material, when it gets entombed in these fine-grained sediment, you're going to tend to have an anaerobic environment, and these features are going to be preserved. And so we're going to come back to fossils when I talk about geologic time, but I do want to put them in their proper context. They are related to fine-grained sedimentary rocks, and they will be preserved in those types of anaerobic depositional basins. So anyway, that gives you a kind of a brief overview of sedimentary rocks and processes. Hopefully that prepares you for lab, and you have a very good week learning about sedimentary rocks and processes. Thank you, and see you next week.